Thank you, Prof. Wang, for the introduction. My name is Zhe Kun. You can call me Danny. I'm from SMART, Singapore MIT Alliance for Research and Technology. So today I'm going to talk about using machine learning to accelerate the material diagnosis, specifically for XRD, X-ray diffraction classification problems. And here we are trying to tackle a common problem we actually have for all the material science in the material science world. Like our data set is small and sparse, so we might not have sufficient data to train our whatever the neural network or supporting vector machine algorithms. So how do we deal with this situation? So my presentation, this is the outline of my presentation. So first of all, I will give you guys a brief introduction of what is XRD and why we need machine learning in the XRD analysis. And later, I will go through the methodology session. So that we will be leveraging a Jupyter notebook to go through the schematics of our method. And lastly, I will share the results of this study. So the work in this study has been accepted. So the paper has been accepted by this year's NIPS conference on a workshop of moleculars and materials. So the archive, we just uploaded the folder yesterday, so it should be available on Monday. We will send you the links of this paper after the workshop. So first of all, what is XRD? What is X-ray diffraction? And what can it do, actually? So this picture is the working principle of the X-ray diffraction. We know that all the materials consist of atoms, and then like all these atoms has certain periodical arrangement. As for the X-ray, because it has such high frequency, it actually has comparable wavelengths with the atom-to-atom distance. So the working principle of the XRD is you incident the X-rays, and then the X-ray got diffracted because of this periodical arrangement of those atoms. And by measuring this phase shift, you actually can extract certain information about this crystal. And in the actual measurement, so we will actually change the angle of theta. So this is basically the incident angle of the X-ray. You actually will change, so like the angle, you will change the angle from 0 to 90 degrees. And by doing that, well, for example, like you can also reduce the number of range for your measurement. And by doing that, you will be able to get a spectra. So the spectra, you can think it as a fingerprints of the materials. So information such as density, phase composition, lattice parameters, space group, things like that can be extracted from this XRD spectra. So this is an example of the XRD spectra of graphite, graphite oxide, and graphene. So you can see, although they all consist of carbon atoms, but because of the atoms is arranged differently, so the XRD spectra actually looks vastly different. So this is in a sense like to getting the symmetry getting the symmetry informations from the crystal by analyzing your XRD spectra. So so for material scientists, it's important to study the XRD because we want to know all those informations within our materials. But it can get complex. So this is an XRD spectra for compounds. So it consists of actually like calcite, like chloride. It's like a mix of compounds. And the traditional way of doing the XRD analysis is what is it called a Rietveld refinement. So you have this spectra, and like a researcher will just be looking at the peaks and the relative position of all the peaks. And by doing that, and then you reference all the peak location and the peak height to a certain database. So this is all done manually. So for example, like for the chloride, you have to be able to locate this small peak, and you say, okay, this corresponds to the chloride peaks, and then I will be able to look that in the database, so I know this is a chloride. So this can be time-consuming because it's all like done manually, and if you have many compounds, you have to do this repetitively. And especially if you are you're trying to discover some novel materials, so you don't really have the reference pattern in your database, then it actually could take hours to do one XRD spectral analysis. So how do we solve this? So we can do it by taking the human elements out. So we can, since this is repetitive work, this is like a classical pattern recognition problem, we can use machine learning to do the classification. And we can do, because the machine is fast, and then we can do this in less than a minute. So the key of success is we have to play around with the input data, so that your measurement data and your measure spectra and the spectra you can simulate, and the machine learning algorithm, like what is the best algorithm for this problem, and also like how do you incorporate your own domain knowledge? If like how would you incorporate like what do you know about this your material and also XRD's measurement into this machine learning algorithms? Okay, so our method starts with data augmentation. So why do we need data augmentation? Because when we are doing this like synthesis of materials, our data points is expensive. You cannot like you cannot say I will synthesize like 2,000 compounds and then use that to train the XRD spectra, because it simply does not make sense. And so for this study, we actually have around like 70 experimental synthesized compounds. This is already taking like months to prepare this data set. But like 70 data spectrum actually is still not sufficient to train, like we found out it's still not sufficient to train our algorithm. So what we do is we did a, sorry about that. So we did a machine learning algorithm. We did a data augmentation. And this is like, I don't know what happened. Sorry about that. So the data augmentation process is very common if you are doing image recognition. So like, for example, we have a picture of a cat. And if we rotate this picture, we still know this is a cat. And if you scale this picture, like enlarge it or make it smaller, we still know it's a cat. So like the idea is, can we do the same thing to the XRD spectra? Well, like physically it doesn't make sense to rotate your XRD spectra. And so what we did is we can do the data augmentation based on what we understand about our materials system. So like, so first of all, we start with the simulation data. So this is the XRD spectra actually you can get from the inorganic crystal structure database. And all the spectra you get is actually in powder form. So like it's something like this. So you have the crystals with all the possible orientations. So there are many peaks actually in this spectra. But in the actual films you make, so like typically it's much easier to make thin films in the lab. And in the same film, there are all those sort of mini crystals, and all these mini crystals have different orientations. So like you could say like for the matter spectra, like this crystal orientation does not exist within this same film. So like that peaks may just disappear compared with like a complete powder spectra. And also like because like the peaks along the preferred orientation will get magnified, so there will be there will also be scaling of the peaks. So what we did is actually we did we applied like 3 layers, which is called peak scaling. So it's simply to scale the peaks randomly with a periodicity in the filter, and also peak elimination. And lastly is the spectrum shifting. So by doing that, you can actually augment your data from like around 200 to like 1,000 or tens of thousands. And then you have sufficient data to train your neural network. So without further ado, let's go to the Jupyter Notebook example, and I will walk you guys through like how we did this data augmentation process, and eventually how we did the classifications based on this augmented data. So this is the general like flow of this study. So first of all, we have both theoretical data and experimental data. And then we did the augmentation based on our physics understanding. So eventually, like all those spectra fit into a machine learning classifier. And then we classify in this case, we are concerned about the crystalline dimensionality and also the space group of that compound. Okay, so let's go to the Jupyter Notebook example. If you have your Anaconda Navigator open, this one, you could launch the Jupyter Notebook. And you can navigate to the folders you downloaded, which is this NUS AMD workshop folder. Okay, so there are like 4 subfolders. So the codes for this study is in the XRD classification. And there's one file called xrddemo.ipynb. So just click that thing. So a quick hands-on, who gets this file open now? Okay, so most of them. Cool. Yeah, just let the crew know, just raise your hand if you have difficulty in opening this file. Let me make it a little bit small. So all of you guys can see the text for this for this example. Okay. So this Jupyter Notebook example is meant to be a relatively self-contained example of doing XRD classification, physics-based data augmentation, and the overall steps are actually 5 steps. First of all, we need to load our data. Well, that's of course the first thing you need to do. And then because the experimental data may contain noise and some background signals, we have to do some data pre-processing. And then afterwards, we will do a augmentation. And lastly, we can use this augmented data to feed into a classifier. So we will have the classification results. And lastly, you can actually do a cross-validation and hyperparameter tuning to improve the results of this classifier. Okay, so let's start. First of all, let's start preload some libraries and functions which we will use for this example. You can just press Shift and Enter to run the cells. This is preload the libraries, and we don't know for this machine learning problem. We don't know what is the best algorithm we can use. So here I will list a list of classifiers from sklearn, and you can just play around and see which is the best classifiers for this problem. So let's just load all the classifiers from sklearn and define some functions to read the file. And we need to normalize the data, so let's just preload some functions doing the normalization of the data, and also the functions doing the augmentation of the data. So just predefined functions. You can just load it. And also define the functions of doing the experimental data pre-processing. Okay, so we have preload all the functions and libraries. Now we can start play around with the data. So first of all, let's load the XRD spectra. So the XRD spectra contain both experimental and theoretical data. The theoretical data actually are parallel XRD, which I have shown in the previous slides. The specific compound formula is not shown because of the data privacy issues. And keep an eye open for the upcoming our NIPS conference, and also the other paper where we are submitting specifically for this for lead-free perovskites. Okay, let's run this session. Load the both simulated XRD spectra and measured XRD spectra. We can take a look at the data. So let's print out the head of the theoretical data. So THEOR, meaning it's simulated data. So you can see this big giant matrix. So the first row of this matrix are the labels. In this study, like in this example, we'll just be looking at the dimensionality of this crystal, meaning if it's cubic or zinc blende, then it's a three-dimensional crystal structure. If it's layer like graphene, then it's a two-dimensional crystal structure. If it's like dots, like quantum dot, then it's it's a zero-dimensional crystal structure. So we want to know this crystal structure based on the XRD spectra we have measured. And so the first row is the label. And then if you look at the two columns here, so the something starts from 5 all the way, actually all the way to something like 90. It's the 2 theta angles, so it's the incident angle of your X-ray. And the second column here is actually the XRD spectra. Okay, so we load the theoretical data. Right now the data is actually in a string form. So let's convert that string. Let's convert the data from string to numbers. Because like for the input of the machine learning, we need numbers instead of strings. Okay, we can plot the theoretical data. You can actually see, yeah, this is like we just randomly pick one of the theoretical data. There's many peaks. The x-axis is the two theta angles. The y-axis is the XRD intensity. So what we need to do first is to do a data normalization, because the X-ray intensity is arbitrary units. And when you feed anything to a machine learning algorithm, you want to normalize your data. You don't want these arbitrary units have any like bias when you are training your algorithms. So what we do is we did some like data normalization, which the function has been predefined here. Well, yeah, here. You can also use a min-max scalar from sklearn, but for us, because we have a specific data structure, so I just write my own data normalization function. If you compare these two graphs, they are basically the same. So only if you're looking at the y-axis numbers, so it's just like I normalize everything from 0 to 1. So we did this for all the spectra, both theoretical and experimental. We can look at the size of the XRD spectra. So we have 2,000, more than 2,000 rows with 1,064 columns. So the rows is the 2 theta angles. So this is like the vectors you input into the classifier. And the number of rows is the number of data points. So we can also look at the experimental spectra. So it has the same data structure. The first row is the labels. And we'll do the same data normalization to the experimental spectra as well. We can print out the size of the experimental spectra. So clearly they have a different size, and also we have less data points. We have 73 rows, 73 columns, meaning we have 73 different XRD spectra. So first of all, we need to unify our data to be able to put that thing into the machine learning classifier. So we wanted to have, so because our x-axis is the 2 theta angles, we want everything to have the same starting and ending point for the two theta angles. So let's trim the data first. Okay, that's just list two blocks of code stars. Oh, sorry, I have to run this first and run this later. Yes, and now we can plot the experimental data. So this is an actual measured XRD spectra. So if you compare your experimental spectra, it is very different than the theoretical one. You can see there are many peaks in the theoretical one. The experimental one, there's many noise. And also you can actually see there's background signal. This comes from the glass substrate when we are doing the XRD measurement. So, so how do we deal with this spectra? We can do a background and noise subtraction. So for this case, we are using a Salvago filter from SciFi package, and then later you can use another function from SciFi. So SciFi is a package from Python by looking for the peaks. So we have predefined this function in the previous section. Essentially, like I think is essentially this function. So we just call that function and run a background and noise subtraction. And we can plot it again. Okay. So that's the post-process experimental data. So you can see after the post-processing, we managed to get rid of the noise in the spectra. And also we managed to pick most of the peaks. And there was one peak missing here. This is actually because of one hyperparameter. When you are doing the pre-processing of the data, you can choose a window size. And the window dictates how many peaks is allowed in that window. If you allow the window to be really big, for example, for this case, so it will just choose one peak within this window. So that's why this second peak here is sort of ignored. These some parameters actually you can tune, and you should tune actually when you are optimizing your classifier. Okay, so so now the experimental data looks a little bit similar to the theoretical data now. But the problem is the theoretical data has way more peaks. It's just because the theoretical data is a powder XRD. The experimental data is a thin film XRD. And then we try to mimic so right now what we will do next is actually try to mimic the thin film behavior from the XRD spectra. So this is our data augmentation process. So let's just start to do the data augmentation. For this case, I will arbitrarily choose, I want to augment my theoretical data to 1,000, also my experimental data to 1,000. Then we can do the augmentation process. So it's run. And we can select one of the theoretical data. This is the original one. And I will show the three filters we have applied to this theoretical data. So for the first filter is the peak elimination filter. So it's a periodical blocking layer which randomly eliminates peaks. So if I just plot it, if you compare the difference of the two curves, essentially the location of the peaks and the height of the peak is still there. It's just for a certain portion, the peaks are gone. Essentially, you are actually applying a filter with a filter, and also you're adding the random state in that filter. So the filter could either block or not block, or let this signal pass through. Okay, that's the first step. And also because there's random state, so every time actually you run this, you actually see this a little bit different. But if you look at the peak, the relative position of the peaks is still stay unchanged. And the next step is the scaling, the peak scaling filter. So that's sort of to mimicking in the preferred orientation of your crystal, the signals will be magnified. If it's non-preferred orientation, it will be diminished. So let's apply the second filter. So if you compare these two graphs, all the peaks are still there, so you are not really get rid of any peaks. But you will see the relative intensity of all those peaks actually changes. This is because we add a random state, also a random scalar. And lastly is if you have strain in your film and also maybe your instrument is not so accurate, you could actually shift, the spectrum could be shaped left or right. So lastly is adding a shift filter. So if you compare these two graphs, that's not really too much different. It's just the peak is shifted a little bit. And you can specify this range based on your understanding of what is the precision of your XRD tool, and also what are the estimated strain within your film. So you can do it in a very physics informative way. Okay. And then we can, this step is to convert all these 0D, 2D, 3D labels, so the previous row you have seen, into numbers, so that we need to compare everything into numbers to be able to train the machine learning classifier. Because there's a random state here, you actually can do this. You can do this whole process many times, and this graph will be just repeated thousands of times, and then you will have thousands of different spectra. So all this spectra later will be fed into your machine learning classifier, which is down here. So now, after data extraction, data pre-processing, and data augmentation, we have around like 2,000 spectra. And now we can start to train our classifier. First of all, let's define, okay, the number of experimental spectra we want to use to train the classifier. So to train the classifier, we'll use a cross-validation method. So the cross-validation, well, like the cross-validation meaning like you can split your data set into 5 folds, and you will use 4 folds to train the algorithm, and the remaining fold to test it. And you will do this iteratively, and eventually you can sort of avoid the bias in your data set. I think Chen Xiao gave a really nice intro on the cross-validation and also how to fine-tune all the parameters for the classifier in our previous workshop. If you are interested, you actually can log into the YouTube channel and look for Chen Xiao's clip, which is, I believe is gradient boosting, decision tree, and PySwarm and Swarm inverse design. Okay, so let's put all the data into the classifier and let's specify the number of the folds for doing the cross-validation. In this case, we will do a 5-fold cross-validation. And we don't know what is the best classifier we can use. So here, like there's a list of classifiers, and you can choose which one. You can choose based on your own choice. And later, of course, you will pick the one which gives you highest accuracy. So for this case, let's use random forest because it runs fast. Okay. And now press Shift and Enter. Oops. I have to run this session as well. Session, and now it should be able to run. Yeah. So just make sure you are running the sections after sections. So like if there's one section which is not run, then there'll be problems. So now it's printing out the accuracy of your prediction for each fold. So we can say, okay, so for the first 4 folds, we get like around like 83.33% in terms of predicting the dimensionality of your crystal based on all this XRD spectra. The last fold is good, but potentially is biased. It depends on the way when you do the cross-validation, when you do the data set split in your cross-validation. So what we can do is we can take an average of this value. And okay, so like if we do the cross-validation with 5 folds, the mean accuracy is 86.7%. So that's just with the random forest classifier. You can also try this with a neural network. So for our study, we actually use a 3-layer neural network with 256 neurons. So the neural network is a dense neural network. And the activation function is a ReLU function. We can run this as well. So load neural network and run this again. So this is gonna take a while, like potentially a couple of minutes for you to run. But bear in mind, like your data set so the data set I gave to you is not the complete data set. So the accuracy you get might not be like the true accuracy compared with what you can have for the real experimental data. If you are interested in getting like the complete data set, you can approach me after the workshop. Okay, it's gonna run a while, but so the last step is what we should do next is actually to fine tune all the hyperparameters, because for all the classifiers, you have many parameters you can tune, which will affect the accuracy of your output. And also when you are doing the data pre-processing or the data data augmentation, there's also many hyperparameters you can tune. So what you should do is to look for the optimal parameters, and in this case we find a 3-layer DNN performs better than other classifiers for both cross-validation, and also we newly synthesized like a validation data set also the neural network gives us the best results. Okay. If we go back to the presentation, so I will just briefly share the results. So yeah, this is the 3 layers we have applied for the data augmentation process. And those are the final results with all the methods and the accuracies. So we can see the neural network gives us the best accuracies. And that's why we pick it. And we also try to play around with the number of augmented data. So we found there's a sort of a threshold. So you need to augment your experimental data to around like 200 or 300 for dimensionality prediction, and to around like 1,000 for the space group prediction. So that's understandable because space group have more labels. For this data set, we have 7 space groups, but for the dimensionality, we have 3. So yeah, and the accuracy, the accuracy for space group prediction is a little bit lower. So the best accuracy you can get is around 84%. So lastly, we actually did a completely different study. Well, it's not completely different. It's more like, so now we have like take out the human elements, and then we use machines to classify those XRD spectra. So what we were thinking is, in the measurement, we always take all those like the measurement in a very fine step size, meaning like we want to have our data as free of noise, like we want to have our data free of noise. But if the machine can do the classification, so how would the noise in your data affect the machine learning's output? So what we did is we increased the step size of the 2-theta scan. So meaning like if we increase the step size, essentially like the data acquisition time, which is drawn in this black line, decreases exponentially with the increasing step size. But if you look at the accuracy, it still keeps relatively okay before the step of 0.16, meaning like previously in our lab, we are always doing this measurement at 0.04 2-theta angles. So meaning like if we are using this machine learning algorithm, we can sort of like sacrifice a little bit precision in the data in the spectra we take, but by doing that, we can actually reduce the time like by quite a lot. Okay, so that's it, and thank you.